In this video, I'll show you how a Totem-Pole PFC works and how you can implement a current controller in order to control the current. So in order to understand this, we first need to look at waveforms and how the Totem-Pole PFC works. So basically, into the Totem-Pole PFC, we have an AC voltage, which is sinusoidal. And then on the output, we have this voltage, which is around 400 volts with some ripple. So the input voltage is measured here, and this is the output voltage. And then, so basically the Totem-Pole PFC rectifies the voltage, while it also controls the current. So you can see that we control the current such that the waveform of the current is equal to the waveform of the voltage. So that is the basic principle of the Totem-Pole PFC. So now, in order to control the current, we actually control the voltage over the inductor. That is how you should think about it. So we know that VL, this must be equal to the change of current over the change of time multiplied by L. So when we control VL, we control the desired change of current that we want. Understood? So the change of current is basically the reference current minus the actual current that we have. So we need to find the voltage that we want. We can also look at this a little bit different. We can say that the VL, voltage over the inductor, is this voltage minus this voltage. So we define the voltage at this point as Vm. So it is something that we can control. We control it basically by controlling the switches, because you can see that the voltage here depends on whether this switch is on or whether it's off. And now this voltage at the other side is surprisingly a bit complex, because it also depends on, so we know that it is VAC, but depends on the reference, because we don't know this point here. It is floating between this point here and then this point here. So you know that when the current is flowing in this direction, all of the current must flow here through this diode, which means that this voltage here is equal to this voltage here. And then in the other direction, we would have that this voltage here is equal to this voltage when the current flows in this direction. I hope that makes sense. So basically, if we look at when the current is positive first, when the current flows in this direction, it becomes a bit easier, because we say that this is ground, so it's 0 volts. So this means that the current flows here, so the current here, voltage here is 0 volts, and then this point is 0 volts, so this point is also 0 volts. So in this case, this voltage here is equal to the input voltage, which is VAC. So when the current is positive, we can write that VL is equal to VAC minus VM. And now we want to try to find VM. So we control VM by controlling this MOSFET here. So the duty cycle is set here, or it's not the duty cycle but the gate signal, but it has a duty cycle. So we say that when the duty cycle of this gate here is 0, we know that this gate is open, which means that the other gate, this one, now it became a little bit messy, is closed, which means that Vm must be equal to the output voltage, which is this voltage. So here, Vm is equal to Vo. And now when the duty cycle is 1, we have the opposite that happens. So now this MOSFET is closed. So therefore, voltage Vm is equal to 0. So when duty cycle is 1, we know that Vm is equal to 0. Now, if you solve for these two equations here, we can make an expression for Vm. So we know that Vm is equal to 1 minus d multiplied by Vo. You can see that this equation here satisfies all these two sets of equations. And now we can insert this for VL. So we have VL is equal to VAC and then minus 1 minus d and then multiplied by VO. So we're making an average model, so therefore we set this to 0. Or we can actually set it to an epsilon, because we want it to be 0, but it might not be 0 if the model is wrong, if that makes sense. So we can now actually solve for the duty cycle. So if we solve this equation, we get the duty cycle is 1 minus VAC over VO, and then we add epsilon. So this epsilon is actually divided by the voltage, but it's still rather small, so it doesn't matter. Now, this is basically the formula for the duty cycle, and this is what we implement in the current controller. So if we go into the current controller, you can see that we have VAC over VO, which is the output voltage. And now this point here, when this one is larger than this one, in this case, it becomes 1. And then here we have the duty cycle, and then this is the error term, epsilon, which we call it. So you can see that the duty cycle becomes equal to 1 minus VAC over VO, and then plus the error term. But when the current flows in the other direction, it becomes a little bit different. But the procedure is basically the same. So now the current flows in this direction, which means that it flows into this diode. So this becomes just a wire, while we can ignore this diode. So now the voltage here is VO, which means that this voltage is VO, which means that this voltage is VO. So the formula for VL is now a little bit different. So we have this voltage. So VL is equal to this voltage here, which is VAC, plus VO. And then we have this voltage, which is VM, so minus VM. So VM is still the same as earlier, so we have 1 minus the duty cycle multiplied by VO. So now if we say that this VL is epsilon, and we solve for the duty cycle, we will get that the duty cycle is equal to minus VAC over VO, and then plus epsilon. So remember that we divide epsilon by VO, but it's still epsilon. So if we look at the current controller again, you can see that when the voltage is negative, because now when the current is negative, the voltage is also negative because they have the same waveform. I forgot to explain that. So when this one here, I need to draw, when this one here is lower than this one here becomes 0. So this is 0. Then this is still the same. It is VAC over VO. And then this is the duty cycle. And then this is epsilon, the error. So the PI controller basically controls for the error. So the duty cycle now becomes minus VAC over VO, and then plus the error. So that is basically how you find the duty cycle in both cases. So I haven't explained this PI controller, but if you look at my other videos, I have a more detailed explanation of that. But the way to think about it is that the feed-forward is correct under ideal circumstances. And then the PI controller corrects for that. Yeah, so that is basically how the Totem-Pole PFC works. Now, if you want the simulation model, you can just click on the link in the description. In my next video, I will show you how you can easily convert this Totem-Pole PFC into a bidirectional Totem-Pole PFC step by step.